Hello, I am Lucas Therian, and I'm going to explain to you how the Math of PID, the PID controller, works. But first, what is PID or a PID controller? Essentially, it's a very tight loop, very accurate control loop that can get you very accurate result. Get a robotic arm in this case to a position very accurately and very fast. The equation for it we're going to be using here is up there, represented by U of t. Well, let's go through these three terms of the PID, starting with proportional, which is the simplest of the three, and it is essentially, so say we have the function e of t here, which represents our error, and which can be modeled as t cubed, just for simplicity's sake. You can just make a control loop proportional to the error, and you can get to your set point, but it won't be as efficient or as accurate with just p. And in the 1920s, people realized this and started making a solution to this using calculus. But first, to explain calculus, we're going to explain the concept of position, velocity, acceleration. It's the best way to explain integration and differentiation, the two core concepts of calculus. So essentially, we have this function here, which is on 1 degree, our e of t function. And essentially, so velocity is the rate of change of position, and acceleration is the rate of change of velocity. This becomes important later on. So derivative. Derivative is essentially the instantaneous rate of change of a function. So how fast it's changing at say here, this function here, e prime of t, represents how fast it's changing, and the first basic rule of derivatives is the power rule, which you can see here. And so we plug in t cubed we get our derivative 3t squared for e prime of t. For our PID equation, d is used to reduce overshoot by moderating the rate of change. So essentially it says, A, you're gonna miss, slow down if it's going too fast, and if it's not going fast enough, so it'll say speed up. And then for our last term, I is used to calculate the area under a curve. Essentially, it's 1 degree higher. And in this case, we apply the power rule in reverse. So our integral of e of t is, in this case, x to the 4th over 4 plus c, which is the constant of integration, which is, in our case, the current error when we apply the PID, enable the PID loop. The purpose of this I variable is to reduce steady state error. So if we go back to our what is PID, and we'll wait for this. To go. And so we see that steady state error there, and then applying an integral term here actually reduces that steady state error, but that also comes with a ton of oscillation. Thank you for watching, and